So, having looked at waves generally and looked at light waves and some of the things we can do with light, namely reflection and refraction, bearing in mind that whatever we can do with light, we can do with absolutely every other wave. So we can reflect sound, we can refract sound. Let's look specifically at sound then. So we're looking at how sound is produced. We're looking at using the particle model to say why sound travels through different media. Media is just the plural of the word medium, and medium means the material the wave travels through. And what happens when that medium is a vacuum, or when you have no medium, because a vacuum is where there is little or no material. A perfect vacuum, there'd be no material, no medium. So here's a little practical for you to do for yourself. Take a ruler, preferably one that's reasonably stiff. Hold it firmly on the end of a table, flick the other end, and make the sound. Describe what's happening. Write that down. Pause the video while you do that. So, having done that, hopefully you'll have said something like the end of the ruler that you flicked vibrated and you heard a sound. So you had something vibrating, and that vibration made a sound which you heard. And that's what happens with sound. Sound waves and lots of other waves travel by causing vibrations, and those vibrations pass out through the material, the medium, and so energy gets transferred. Remembering that's what waves do, they transfer energy. So this particle vibrates, which makes this particle vibrate, which makes this particle vibrate, and so on. The vibrations pass down through the particles of the medium. The particles themselves don't go from here to here, but the vibration does, and so the energy does. And there you go. So here's an animation of that. Here we have a vibration being caused perhaps by a guitar string. As the string comes forward, it squeezes the air particles, and that high pressure area where the particles have been squeezed together passes out through the air. And then the string comes back and it pulls the air particles further apart, and then comes forward again and it squeezes the air. So you've got high pressure area, low pressure area, high pressure area, low pressure area passing through. And these reach the ear. And the ear has an eardrum inside, a layer of skin that's tight, and it vibrates. That vibration then gets passed to the middle ear and gets converted into electrical impulses, which get sent to the brain. So sound travels at different speeds. It travels at 330 meters per second through air, typically. Travels at about 1 kilometer per second through water. Travels about 5 kilometers per second through steel. So different speeds in different media. Light travels at 300,000 kilometers per second, about 1 million times faster than sound in air. How do we know that sound travels much slower than light? Well, if you're watching a fireworks display, you'll see the first flash and then you'll hear the bang. Thunder and lightning is a little harder to tie down like that, because you don't know whether you're seeing the first flash or the second flash or what you're seeing. But the sound does travel much more slowly than the light. The light is more or less instantaneous. It gets to you pretty much as it's made. the sound travels at 330 meters per second, so it takes about 3 seconds to cover a kilometer. So, this is a picture of Concorde. Concorde was the first and only supersonic passenger aircraft. That is to say, it could travel at twice the speed of sound. It doesn't fly anymore. So, some questions for you. And the answers to them. So, what is a vacuum? Well, a vacuum is where there's little or no material. Basically, it's an empty space, no particles. That's a perfect vacuum, no particles. Real vacuums have very, very few particles in them. So, when there's air inside the bell jar, this being a bell jar, you can hear the sound coming through. The air vibrates, that makes the bell jar vibrate, which makes the air outside vibrate. And as we discussed earlier, the sound gets to your ear. But when you turn on the vacuum pump, you remove the air from in here, so the vibrations can't pass from the beater on the bell through the air to the bell jar. And so you don't hear the sound so well. Now, vibration does pass. In this particular example, the bell jar is sitting on a table and the vibrations would pass from the bell through the clock, through the table, and you could hear it that way. So you still get some sound coming out because you can't get rid of all the vibrations, but you can tell that the sound is reduced. So here's a video of exactly that experiment. So, hopefully in watching that video, you saw that as the sound of the bell, as the pump ran, the sound of the bell got less and less noticeable. When he turned the pump off and disconnected it from the bell jar, you could barely hear the bell at all. Then he allowed the air back in, and the sound of the bell increased. So you could tell that as the air was removed, the sound got quieter, and as the air was replaced, the sound got louder again. So from that, we can see that the air is absolutely essential to hearing the sound. So here you have the oscillations on the left-hand side, the hand. Let me just take that back a little. The hand is moving from left to right, and you see the energy being transferred through the medium, in this case the slinky, from left to right. So this is a longitudinal wave. I'll go back a little bit further there now to show you. There's the compression, the high pressure area. And here you have the rarefaction, the low pressure area. You can see the coils, the particles of the medium in this case are pulled further apart. So this is a low pressure area. It's called a rarefaction. And the high pressure area where the particles are squeezed closer together, that's your compression. So sound is a longitudinal wave. How then are the properties of the wave and the sound we hear connected? So you can see as the pitch of the note increases, watch what happens on the oscilloscope. You can see that the frequency of the wave is increasing. Now, this looks like a transverse wave. It isn't. What's happening is that this machine, the oscilloscope, what it does is to cause a bright spot to move across the screen. And what this does, the signal generator, it makes the spot move up and down at the frequency that's set on here. So as the spot moves up and down, it moves across the screen and you get this nice wave pattern. So it isn't a transverse wave, but it allows us to see how, as we change the frequency, how we change the amplitude, as we will do later, how that affects the frequency and the amplitude of the wave. So as we change the loudness of the sound and the pitch of the sound, we change the amplitude and the wavelength of the wave. So there we have changed the amplitude of the wave. You see the wave getting bigger and smaller, the amplitude being the maximum displacement from the rest position of the particle of the medium. You can see that as the sound gets louder, the amplitude of the wave causing the sound gets bigger. Now that distinction is important. The amplitude and the wavelength or the frequency, these are wave properties. The loudness and the pitch, these are sound properties. So if you're talking about sound, talk about the loudness, talk about the pitch. If you're talking about the wave causing the sound, talk about the amplitude, talk about the wavelength or the frequency, frequency and pitch being the two that are connected. So there we're increasing the pitch, decreasing the loudness, increasing the loudness, increasing the pitch, and you can see throughout all of that the effect it's having on the wave causing the sound. This is a video about the connection between the wave causing the sound and the sound that you hear. So here I have some axes. On this I'm going to put some waves, and I'm going to describe the wave and the sound that the wave would make. So let's look at a wave which has a low amplitude, so you can see the peaks and troughs are not very big, and a low frequency, so there's not very many waves on here. Now these are in arbitrary units. I don't have any values on here, but I'm saying this is a long period of time relatively, so there are few waves. It's a low frequency. And what you have then, because you have a low amplitude and a low frequency, the low amplitude of the wave means you have a quiet sound. The low frequency of the wave means the sound is low pitched. So the amplitude of the wave is about the loudness of the sound. The frequency of the wave is about the pitch of the sound. So if we then looked at this wave, well, here we have a big amplitude, but again, we don't have very many waves on my axis here, and so this is a low frequency. So here we have a high amplitude and a low frequency. Because we have a high amplitude of wave, we have a loud sound. Because we have a low frequency of wave, we have a low pitched sound. So then let's look at, here we have lots of waves on the screen. We have a high frequency, but again, we don't have a very big amplitude. The peaks and troughs are quite small. And so what we have here then is a high-pitched sound because we have a high frequency of wave, and a quiet sound because we have a low amplitude of wave. Here we have a high amplitude and a high frequency. Lots of waves on the screen here and big peaks and troughs. And so we have a loud sound and a high-pitched sound. So those are the connections between the loudness of the sound and the amplitude of the wave causing it, the pitch of the sound, and the frequency of the wave causing it.